Thank you very much for inviting me along today to speak to you about tidal energy, and thank you for the very kind introduction. The structure of what I'm going to talk about today is really broadly to talk about tidal energy in general. Why do we think tidal energy has a very special place within that future renewable energy mix? No question in our mind that the future is a mix of different renewables all working together, but we think tidal's got a fairly special place within that mix. Then to talk about what Open Hydro has been doing around developing our technology. There is a lot of technology development in our sector, and I'm best placed to talk about our developments and really what we've been doing around commercialising tidal energy. That programme of research and development has led us to a number of commercial developments, of which Liam would have mentioned. So I'll give you a little bit of information about each of those projects. But I think what's important to say is each of those projects is a stepping stone to very large commercial arrays. Each partner we're working with is really testing out, doing pilot projects, which then lead to these large, multi-hundreds of megawatts installations. A couple of slides just about our company and how we're structured, and then really move to the final part, which is the financials. This is all about delivering a cost of energy which is acceptable to our customers, and our customers are traditionally utilities. So we have to demonstrate that we've got a technology that not only works, is kind to the environment we're operating in, but also delivers economic returns. And I can talk a little bit about that. So jumping straight in, why do we think tidal energy's got a special place within that renewable energy mix? And I think it's probably important to say is if you work for a company like Open Hydro, you're pretty well certainly going to be a passionate believer in all forms of renewables. So this slide is in no sense intending to knock other renewables. This is just emphasising why we think tidal is a special place within that mix. So giving three fairly straightforward measures. The first of all is predictability. Tides are generated by the sun and the moon's gravity. Because the position of the sun and the moon can be predicted with ultimate accuracy, that means the resulting tidal flow can be predicted. So our technology is a little bit like having a wind turbine that you know when the wind's going to blow, you know how strong it's going to blow, and in what direction. If you knew all of that, you'd be able to forecast the power that's coming off that wind turbine. And we're not talking about being able to forecast this a couple of days in advance. We're talking about being able to forecast this to the minute, decades in advance. So a very predictable form of renewable. The next feature is energy density. Water is 830 times denser than air. So we're talking about relatively compact technology. And the final part, which is possibly on the softer side, but really of crucial importance, is around the acceptance of the technology. We're proposing turbines that sit on the seabed. You can't see them, you can't hear them, and they don't interfere with shipping traffic. They're deep enough not to interfere with shipping traffic. So the result of that is you get very little barrier to the communities that are based near these installations, which I think is a very important feature for renewables. We already have consent for projects in Scotland, in the Channel Islands, in France and in Canada. We're going through consenting in the US at the moment, and a common theme that we're getting is that this is a form of renewable energy which people like. It doesn't have a huge impact on them if they're based near it. So in one slide, in one animation, this really sums up Open Hydro's vision for tidal energy. So it's a turbine mounted on the seabed supported by a frame, and for 6¼ hours, like clockwork, the tide flows in one direction. At the end of that period, the tide stops and it flows back another way for 6¼ hours. Just like clockwork, to a very sort of metronomic cycle. It does that day after day, week after week, year after year. The amplitude, so the speed of that cycle varies around the lunar cycle, which is a 14 or 28-day cycle. But all of that is fully predictable. So we have that form of predictable energy. And I think anybody that's involved in wind energy would recognise the benefit of this. Typically in a wind site, you'd be looking at 1 to 2 years of met mast data, so putting a mast up to record the wind speeds for maybe up to a couple of years. We have the huge advantage that we only need 28 days worth of data to characterise a site. So what that means is putting a device on the seabed, a device called an acoustic Doppler current profiler. It's a device that measures water speed acoustically. And we measure the speed and direction of the water up through the water column to a high degree of accuracy over 28 days. Once we've measured that 28 days and we've recovered that device from the seabed, we can then use a mathematical technique, a harmonic analysis, to then project, well, what's that site going to do into the future? So once we've done that, we've then got a model that says this is what this site's going to do for the next 10 or 20 years, depends how long we want to extrapolate that analysis. We can then overlay that with a turbine generation model and say, well, what would our turbine do in that tide? And that gives us the yield from a site. So whereas some form of renewables, you're having to sort of make some kind of assumption or best estimate as to what you're going to get in terms of yield from that site, we have that to a very high degree of accuracy, which makes it a more predictable form of investment as well in terms of developing. So the next section, I'm going to talk a little bit about the technology that we're developing. And I'd be conscious that last time we did a trawl of technologies in our sector, there was nearly maybe 50 companies that were developing technology in the sector that we're in. So it's a very active area. You could take that as a negative if you're in the sector, but actually I take it as a positive. I think if we were the only people in the world doing this, we'd probably ask ourselves a question, why are we the only people doing it? So the technology we're developing is called the Open Center Turbine. And probably if there's one message that I'd like to leave about our technology, it's around simplicity. We believe that if something's going to survive in a very harsh, very aggressive marine environment, the best outcome is something that's going to be very simple and very robust. We, as engineers, would recognise that we could do all sorts of clever things to our turbine, have blades that pitch around, make the whole thing yaw underneath the surface of the water on the seabed. But all of that would result in a higher cost, so a higher capital expenditure, but more importantly, a higher maintenance requirement. So we need to interact with the machine more often. Every time you go in, every time you leave the harbour in this environment, it's expensive. Working in the marine environment is expensive. So we've gone down the road of saying keep it very simple, keep it very robust, and minimise that impact. So how the turbine works, simplicity again is the theme. So we have a fixed outer ring and a rotor that spins inside that. So as water flows into the turbine, the inner ring rotates, and we use what's known as a permanent magnet generator to extract the electricity. So we're going directly from motion of water directly into power offtake. And you can actually see permanent magnets embedded around the circumference of the rotor, and then the generator assembly is within the stator. So that makes it very simple. We don't have any conventional drivetrain such as a central shaft which needs bearings and seals or a gearbox to increase the outtake velocities. So it keeps it very, very simple. And we've proven in terms of scalability that the turbine can be built. So when we started, we were working with 35 kilowatt units, so quite small units. We subsequently scaled that up to 1/4 of a megawatt, and most recently we've installed our first 1 megawatt unit. So we're now moving into the territory that we see as a commercial scale tidal turbine. But as I mentioned in the opening, it's all important to have a technology that works, but it's as important to demonstrate that it doesn't transfer problems from the land, such as oil and gas generation, and then start to create environmental problems in the ocean. It's crucially important that we can prove that that doesn't happen. So the turbine has a number of design features that support interaction with marine life. So a large open centre to allow marine life to pass through the turbine unhurt. And that's actually quite similar to a lot of dam technology that's being developed, particularly in areas such as the US. It's got no oils and greases and lubricants that could cause a pollution risk. And the blades being within the device help make it more visible. But the truth of it is for all those design features, we video underwater all of our testing at our research centre in Orkney. And we've never seen a fish or a seal or a dolphin or a whale or a shark or any marine life swim through our device or interact with our device. And I would be an engineer, as Liam would have said, so I'm better left to answer those questions to the marine biologists. But what they tell me is that these creatures, marine life, are far too intelligent to swim into rocks. They don't swim into boats. So why would they swim into a turbine? And that's the body of evidence that we're building. There's also the counter-argument that says, well, therefore you're scaring marine life away from their natural habitats, so areas where they would feed or where they would migrate through. And what we're finding is that isn't the case either. So the research centre where we're based is monitored independently by the European Marine Energy Centre, and we're not seeing behavioural changes in the site. And we've identified it's got a very low acoustic signature, this turbine underwater, just enough, in my opinion, to act as enough of a warning for marine life to swim around the device. So we're building up a very strong body of evidence that demonstrates that there aren't problems with this type of technology in the water. So what have we been doing around testing this technology and developing this technology? We selected the European Marine Energy Centre, EMAC as it's known, as our location to do our R&D. And the reason for doing that was that EMAC was created by predominantly Scottish government funding, but also UK and EU funding, predominantly to develop and promote the development of the wave industry and the tidal industry. And clearly we're focused on the tidal side of that. They've created a test centre where they've laid cabling on the seabed. They've got a grid connection on the shore, so a substation with a grid connection, and also an overriding consent that this is an area where these types of devices will be deployed for research and development work. So it's a bit of an easier step into, rather than going into a fresh site on our own. It is no soft option. It has got not only some of the strongest tides you can find anywhere in the world, up to 8.5, 9 knots, but also the weather climate in the Orkneys is just ferocious. I don't know if anybody's ever spent any time off the top of the north coast of Scotland, but it's almost impossible to describe what a gale in Orkney's like. It's just phenomenal. There are no trees in the Orkney Islands, and that's for good reason. What we've decided to construct there is quite unique, and it's very different to how we see turbines installed commercially. I talked about that we see a vision of turbines mounted on the seabed. Well, this structure clearly is a surface-piercing structure, and that's for very good reasons. As Liam would have mentioned, the early part of my career was in the automotive sector, and if you're designing a new family of engines for a major automotive company, you build a number of prototype units and you put them into an engine test cell, connect them up to a dynamometer, and you run them at different temperatures, different loads, different fuels, and you learn about that technology. And this is what we wanted in Orkney. So it's a structure that allows us to raise and lower the turbine using some hydraulic winches. That gives our engineers the ability to access the turbine and look at how it's performing. But more importantly, the ability to take one turbine off and replace it with another one. That gives us the ability to iterate. And if we'd gone straight for a turbine directly deployed onto the seabed, we wouldn't have had either of those benefits. We wouldn't have been able to interact with it, and we wouldn't have been able to replace it as we learned about the technology. So very important for us. However, it does carry for us a bit of baggage in the fact that it's a structure that's surface piercing. It's not the most beautiful structure to look out at from your house. So that's something that we've had to contend with. In constructing this piled structure, I think it's simple to say it's the hardest thing I've ever been involved in. It's installing two large piles drilled and grouted into the seabed, which doesn't seem particularly challenging. However, we're doing this in a tidal site off the north coast of Scotland. The type of equipment we needed to use were jack-up barges, 2 of them, one as a lifting platform and one as a drilling platform. And if anybody knows anything about the marine market, they'll recognise that this equipment is very rare, it's very expensive, and also it's very limited to the water depths it can operate in. And that's just to do with the length of the legs, how much they can self-elevate. So it creates an awful lot of challenges to construct this way. However, we completed the construction, and then we also completed the connection of the structure to the 11 kV UK national grid. And that again was a very complex operation. We had to move 0.5 kilometre of subsea cable to connect it to the structure and complete an 11K grid connection. And that would be the first time that a tidal turbine had been connected to the UK grid. The result of all that is the testing itself, and this is the video that I talked about. We have a camera that's underwater that can video all of our testing, and you can see very clearly that you can identify that there's no marine mammals or fish swimming through the turbine, and we can monitor that very closely and build up that library of evidence. So as I mentioned, we connected it to the grid, and in early 2008, prior to 2008, we installed the structure actually in 2006. So between 2006 and 2008, all the power we generated was dumped into a load bank, and that's actually the structure that you can see on top of the control room. From early 2008, we completed the connection to the UK grid and actually exported power into the UK grid. And that was we were the first tidal company to achieve that milestone. Very, very important milestone for us as a business, but I think also important for this industry as a whole. We're in an industry, in a potentially very large industry, and it's these sorts of successes that we and other parties in the industry need to be achieving. Using the structure, we've continued the R&D program that I've talked about. So actually, since 2006, we've actually tested 4 6-metre tidal turbines on the piled structure. So typically every 9 months we go through a cycle of testing a turbine, learning from that turbine, feeding that learning into the next unit, and then testing that. So trying to rapidly iterate the turbine technology to achieve a stage of commercial maturity, a stage that we can start supplying it to customers. And that's a very important thing to be able to do. A question that's often asked of me is, well, what has changed between the very first turbine and the current turbine that we're testing? And really, the main things that have changed with our technology have really been not the turbine concept or the design of the turbine. It's all been really about how we manufacture and deliver it. So to give you an example, the first turbine we tested in Orkney was a hand-built unit. It took around 9 months to construct. Being a hand-built unit, the repeatability, the ability to build more than one the same, was really non-existent. And probably you'd argue then that the quality was low. If you jump to where we are today, it's a totally different place. We now source our turbine components externally, and our supply chain would extend through China, South Africa, North America, the UK, mainland Europe, and a lot of components out of Ireland. So we bring those components together, and we now more assemble our turbine rather than manufacture it. The result of that is that repeatability, the ability to build more than one the same, is now there. The quality has improved dramatically. And also, more importantly, the time to build a turbine has reduced dramatically down to around about 8 weeks. We've still got a long way to go, but we feel we've moved the turbine technology from more of a sort of a handcrafted prototype R&D environment now to more of a commercial product. So the lessons learnt from our testing work. The testing work has allowed us to rapidly develop our turbine technology. However, it also highlighted probably one of the biggest challenges our industry have, and that's around installing turbines. And to put that into context, looking at the picture there of the finished product, the white turbine on there, it's a 1/4 megawatt unit, and it costs us around about 250,000 euros to construct that turbine. The piled structure cost us 6 million euros to construct. And so if you put that the simple economics, if it costs you 6 million to install a 1/4 megawatt unit, we don't have an industry. So that really, we knew that from the outset. However, we knew we needed to develop a system to deploy our turbines almost as importantly, if not more importantly, than actually developing the turbine technology. And that brings us on to the second part of our technology development. So I mentioned that the vision for the company was a turbine that was mounted on the seabed without the visual impact and sitting there very securely on a steel frame. And the concept that we came up with to deploy that turbine was, rather than try and position ourselves on site in a very, very aggressive marine environment, is actually to do all the work in the harbour, in a nice, safe, secure operating environment. So assemble the turbine, attach it to the frame, fully commission it, and carry the whole unit to site using a specialist deployment barge and deploy it in a very simple operation. It took us 3 months to build our piled structure, a very long period of time. Our target for this installation was to be able to complete the same operation, but within 6 hours. And the reason for 6 hours is if we take longer than 6 hours, we have to cope with the tide coming back the other way. And that just adds another layer of complexity onto the whole operation. So we continued with a program of research and development around the deployment, and this has really been a focus of the last couple of years in terms of our technology development. So this is the steel structure that we constructed, and we built this at a shipyard in Scotland. And we were supported very generously by the Scottish executive in a lot of this work financially. We also had to develop the marine equipment to install this structure. This type of marine equipment doesn't exist in the general marine market. So our engineers had to design a catamaran barge, a heavy lift catamaran barge. We then had to go through the process of constructing this, and we used a shipyard in Holland to build the structure. But also we had to achieve certification. We can't obviously go out into the marine environment without a fully commercial, fully registered vessel. So we had to go through the full certification for use of this product for installing tidal turbines. We worked with a group called Bureau Veritas that had to develop the standards that needed to be applied to certify this for international use. And this barge has not only now been used in Scotland, it's now also being used in Canada, where it currently is moored. We then connected the turbine to the frame and attached that to the subsea, to the deployment barge. And then this is us towing the barge and the turbine out to site for its very first deployment trials. The next bit of video here is actually just a few minutes before we actually deployed our very first turbine onto the seabed. And I think what's interesting to note here is that we're actually stationary over the seabed. The water that's flowing through there is the tide. And because the tide stops for such a short period of time, these are the kind of operating environment we have to work with. We have to work when the tide is flowing like that. And that means we've had to develop lots of different techniques to allow us to achieve that both successfully, but more importantly, safely. And this is the final product. This is the frame and turbine actually embedded onto the seabed. Really, there were two things we were trying to test from this program of work. The first test was, could we actually deploy a turbine onto the seabed safely and accurately? And we proved that with our very first installation. The second thing we're trying to prove is, does that structure remain in situation? Does it stay there? Does it fall over? Does it slide along the seabed? We would have carried out an enormous number of calculations and engineering studies to confirm that it wouldn't do it numerically, but there's no substitute for actually prototyping this and testing it. Well, that structure's now been there for a year and a half. We monitor it very closely, and we've had absolutely no issues with it. It's stayed absolutely exactly where we've deployed it without any issues. So what does this mean? I said that and I think it's quite interesting when you have the piled structure in the background that took us 3 months. We were aiming for a 6-hour deployment with this new approach. The actual time it took us to deploy our turbine from being on site saying, right, we're ready to go, to having it released on the seabed was actually 20 minutes. It was a very, very short deployment window. And in terms of accuracy, we're able to deploy these within a couple of meters of our target location. Bear in mind, this is a sort of 25 meter by 25 meter structure. We're able to deploy it to almost pinpoint accuracy. And crucially also, we're able to align it to a high degree of accuracy. We want to align it with the flow of water. So it's important that we can install it accurately, and we can deploy these turbines to within half a degree of accuracy. So really, the whole program demonstrated that not only could we deploy turbines safely and securely, that the structures would remain in situation, and we could do that very accurately. This has transformational impact on the economics of tidal turbines, as you'll see later on. But to give you a flavour, if we're to deploy a turbine using a piled structure, and we extrapolate that to a megawatt, so to install a megawatt unit on a piled structure, we would recognise that would be something around 24 million a megawatt to install a megawatt class piled structure. We just recently completed our installation in Nova Scotia of a 1 megawatt unit, and it cost us 3 million. So we've taken a huge amount of cost out of deploying tidal turbines, and that clearly has a transformational effect on the economics of tidal energy. The other thing to probably comment on is, our vision is not to deploy 1 or 2, niche turbines in a few locations. It's about developing tidal farms. And if it takes you 3 months to deploy each unit at huge amounts of cost, it's hard to see you deploying 100 megawatts of tidal turbines. However, if you can deploy 1 in a day, for argument's sake, you can see a situation where you can roll out a lot of tidal turbines quickly. You can have multiple barges operating in tandem in a site. So you can really have something very flexible around how quickly you roll out your tidal turbines and delivering it at a good cost. So we think that's essential in terms of developing our industry. So that's what we've been doing over the last few years around developing tidal technology. The next section is really all around, well, what's the results of that? Where does this now go in terms of commercial developments? So just to describe a little bit about Open Hydro's approach to the market, within our group we have 2 businesses, 2 quite distinct businesses. The first of which is a very standard technology business, very similar to somebody like Vestas or GE Wind or Siemens Wind. It's a business that designs, manufactures and installs the product to our customers, and they're typically utilities. The second part of our business model is around actually developing or being involved in the development of some of the tidal farms themselves. We recognise that we have a leading technology, and that's giving us access to some of the best tidal resources. So we have a business model which is also being involved in some of that development, as you'll see as we step through the examples. So the first project is actually one that's now complete, and that's with Nova Scotia Power. The project came about following Open Hydro responding to a request for information back as early as 2006. And in early 2007, Nova Scotia Power selected Open Hydro following a competitive technology review and due diligence, and selected Open Hydro for a 1 megawatt project in a region called the Bay of Fundy, which is, I don't know if people have come across the Bay of Fundy. It's the site that's got the highest tidal range anywhere in the world. It's around about 17 metres of tidal range. It's absolutely phenomenal. It's like an ocean emptying and filling every 6 hours. I think there's a statistic, I don't know how true it is, but a statistic that says that more water flows in and out of the Bay of Fundy every day than flows out of all the freshwater rivers in the world combined. It's that amount of water. It's enormous. So the project was to develop and install a 1 megawatt unit. And this is some pictures of the turbine that we constructed at our technical centre in Greenore, County Louth, just near to here. It's a 10-metre unit, so it's a larger unit, and that's how we get the megawatt rating on it. And on the left-hand side is a picture of that turbine in the hold of a ship, just being ready to be shipped to Nova Scotia. Probably an interesting thing to note is in the background, you see the black sort of containerized shaped units. That's actually our deployment barge. Our deployment barge breaks down into 17 modules that can then be shipped anywhere in the world and within a day reassembled again. Gives us tremendous flexibility to operate in multiple jurisdictions. This is the turbine fully assembled on the quay side. What we did, which makes obvious sense, is the steel component, the subsea frame. It makes total sense to manufacture that in market. So in this instance, rather than transporting a large amount of steel across the Atlantic, we had a shipyard in Nova Scotia and Halifax that constructed that for us. And that's a model that works well in terms of bringing, with our projects, some local content to the project. And then finally, the day of installation. This was the first time we'd ever deployed a 1 megawatt unit. It's the first time we'd ever worked in the Bay of Fundy. It was the deepest site, around about 50 metres of water depth that we've worked in. So a lot of firsts with this project. The result, though, was we actually even shortened our deployment time. The actual deployment time for this project was 18 minutes from start to finish, and again, to an extremely high degree of accuracy. So again, we've proven that we can deploy turbines quickly and accurately in the tidal sites. So Nova Scotia represents to Open Hydro our first revenue feeds into the business. Prior to that, all of our money was money out in terms of R&D and development work. Nova Scotia Power was our first revenue feed into the organisation. The next project we have is with EDF, and a very similar process. EDF would have conducted a fairly detailed due diligence, technical due diligence, and selected Open Hydro as their technology partner. The project is actually to install 4 16-metre turbines. So this is a further scaling up of our technology. We've gone from 3 to 6 to 10. Next step for us is 16. And in terms of what that means, the larger the turbine, the more power we can produce, and that also helps the economics. And on the next slide, I have a little bit of video, which hopefully you'll be able to hear okay, which is just a little bit of video showing EDF's project.
Predominantly granite rock, and the geophysical investigations confirmed the absence of sediments. The Paimpol-Bréa project plans to install 4 turbines developed by the Irish company Open Hydro. The turbines have a large open centre, which provides an exit route for marine life. They will be mounted on gravity-based foundations, which will be deployed directly on the seabed, which remove any requirement for seabed preparation. Such characteristics mitigate environmental impacts.
So part of the relationship we have with EDF, as well as us supplying EDF with turbine technology and the installation of those turbines, we're also working collaboratively with EDF in terms of optimizing our technology. EDF would have a large hydro engineering division within their group. I think they have around 110,000 employees in total, and within that they've got a very strong technical focus. So we're working together on some minor optimization design changes to the turbine technology, which will lead us to an improved yield from the turbine. However, we're not going to just build our first 16-metre machine and hope we've got our answers right. So what we're currently doing, even as we speak, is we're testing a 6-metre scale version of the EDF machine at our test centre in Scotland, in the Orkneys. And that's allowing us to learn about how these design changes will impact the 16-metre machine once it's constructed. And we start constructing the first of these machines later this year. So moving on a little bit, the first 2 projects really are around us supplying technology to to utilities. The next project is really more around being involved in site development. Typically, the seabed is owned by the state, and in the case of the third largest of the Channel Islands, there's Jersey, Guernsey, and Alderney would be the third largest. A business was created called Alderney Renewable Energy, which together with Open Hydro's support has secured a very long lease on the seabed rights to Alderney's waters, which contain an enormous tidal flow, a tidal race. It's, in terms of potential, you could see anything from something like 3 gigawatts of power come from that one site. It's an enormous amount of energy could come from that one site. So Open Hydro and ARE are working towards partnering with parties that can then develop that resource and export that power most logically into the French grid, which is only a matter of a few kilometres away. The next relationship is also around developing sites which then lead to large-scale turbine arrays. And as Liam would have mentioned, this was announced just a couple of weeks ago by Scotland's First Minister, Alex Salmond, which is that Open Hydro had been awarded a 200-megawatt lease on the seabed in an area called the Pentland Firth. You may be familiar that in offshore wind, there's been in the UK 3 rounds of licensing of offshore wind. And that's the leasing of the seabed rights to parties to develop wind farms offshore. Well, this is the first round in wave and tidal. Open Hydro partnered with SSE Renewables, Scotia and Southern Electricity, in a joint application. And this is a very good model for us. This is bringing the experience and financial strength of a large utility and Open Hydro's technology together, applying for a lease to then build a very large tidal farm. And this is what we're after in terms of all our projects. It's looking at developing scale and developing large-scale tidal farms. The final piece on our map is a company called SNOPUD, Snohomish County Public Utility, that are based near Washington State, near a region called the Puget Sound. Again, this is an area that's got tremendously large potential for tidal energy. And with SNOPUD, we're working towards a small pilot project which then proves out the development of tidal in that site. And each of these projects really is around scale, as I said. So the question is, what about Ireland? I think it's fair to say that as a business, we've not chosen not to work in Ireland. We've been very much reactive to the approaches that we've received. We've not gone out and marketed our product. And these examples that we've already got demonstrate the partners that we feel are the best place to deliver what we're looking at. So we believe that Ireland does have a good tidal resource. We think that some of the assessments that have been completed around Ireland would perhaps be a little bit on the low side. We think a number of the areas that have been excluded for various reasons, maybe navigational or too deep, would actually be prime for our sort of technology. So we think that actually the resource in Ireland could be upped in terms of potential to maybe around about 10% of Ireland's energy requirement. And what does that mean, I think, for Ireland? I think there's really 2 benefits that could come from the type of work we're doing within Open Hydro. First of all, we believe that we could be a world leader in tidal technology. We're in a position where there's only 2 companies in the world that have got megawatt-class tidal turbines installed, ourselves and a company called Marine Current Turbines. So we believe that we've got the potential to create a very much a sort of an export-driven industry in tidal energy. But also, the flip side to that is we can also generate a large amount of energy for Ireland within Irish waters. And we've said that we believe that could be around 10%. So there's 2 benefits of the type of work we're doing. And in terms of the world map, we've talked about some of the developments that we've followed, principally in North America, so the US, Canada, and in France and in the UK. And we've really focused on those markets because of their maturity in terms of regulation and access to very large Tier 1 resources. However, tidal is a global resource. Just last week, myself and some colleagues were in China for a week, meeting with a state corporation that has got access to enormous amounts of energy, enormous amounts of tidal resource. And these are the sorts of opportunities that a company like Open Hydro has in this very much emerging industry at this time. So just to give you a couple of slides about Open Hydro as a company, and then we go on to the financials. So the company was formed in 2004. It was formed following the acquisition of the technology rights to the turbine technology by our chairman and largest shareholder, Brendan Gilmore. And Brendan would have recruited me directly to lead the business from early 2004. We now employ 40 people in the business. We have a technical centre, which is the majority of our people are based, which is our engineering staff, so mechanical engineers, electrical engineers, marine civil engineers, manufacturing engineers. We're very much an engineering-driven company. And we also have an office here in Dublin, which is really more around our administration, so our sort of finance team, our legal team. And we have project offices in Scotland and Canada that look after our projects. And here's a couple of slides just showing the facility we have in Greenall, which really is where the heart and soul of our business is. And these are some turbines that have previously been tested. The one in the centre is actually a turbine that would have tested at EMAC, and that actually was the turbine that was the first turbine to ever generate power onto the UK grid. So a typical model for us is after we've tested a turbine, it's to bring that turbine back to our facility in Greenall, strip it down. You can learn a lot by stripping a turbine down and seeing how it performed, and then we finally put that turbine on display. And this is a view down the other end of the facility. These large horizontal turntables, they're the tooling that we use to manufacture our turbines, and that's tooling that we've had to develop as well. And that's how we manufacture the units. In terms of recruiting and developing our team, we're in a new industry. I keep saying it's a new industry. We can't go out and recruit tidal turbine engineers. There aren't any available to us. So what we have to do is we have to try and recruit from companies where we believe the skills can be transferable into a company like Open Hydro. So you'll see some very relevant names. So, for example, recruiting people from companies such as Vestas or E.ON or Rolls-Royce can bring tremendous access to industry knowledge and engineering. And, for example, our engineering manager actually joined us, he'd previously been there for 12 years from the McLaren Mercedes Formula One team, where he was head of engine quality for the Mercedes part of McLaren Mercedes. So we're able to recruit very skilled, very highly qualified engineers into our group. And that's, as any business knows, the key to any business is the people. So finally, moving on to the financials. As I said at the outset, this is all about delivering a cost of energy that is attractive to our customers. And if we start back where we were in 2006, our sort of reference cost per megawatt was around about 24 million a megawatt installed, which is an enormously expensive cost. And really, it's very hard to see how you're going to make something economic if it costs you that level of capital expenditure. Over the last couple of years, predominantly through how we've re-engineered the whole deployment system, but also in scaling the technology, we're now at a referenceable 3 million a megawatt. That's not a projection into the future. That's actually where we stand today. That's a referenceable cost from our project in Nova Scotia. Where do we intend to get to? Well, our target is to get to 1.6 million a megawatt. And we believe that that's a wholly achievable target, and we've got very clear plans in place on how to achieve that. For example, some of our suppliers would be saying to us, at the moment our procurement is really one component at a time. It's a very inefficient form of procuring. Our suppliers are talking to us and saying if we could procure, slightly more volume, we could be looking at 30 to 50% price reductions as they're able to tool up, gear up for our manufacture. So we see that that's a wholly achievable target. What does that translate into, though, the all-important cost of energy, the cost per megawatt hour? Well, I think the perception in the market is that tidal energy and wave energy are up at this very, very expensive end of the scale. And I think if we were still looking to deploy turbines on piles, that's exactly where we would be. Probably even this is flattering. By re-engineering the way we deploy our turbines and also scaling our turbines, we've brought our cost to 117 euros a megawatt. What does that mean in terms of a cost of energy? That's pretty equivalent to offshore wind prices. So our entry point into the market, now this albeit is at building some scale, building some larger, this wouldn't work for one or two turbines, this needs to be at the sort of 50 to 100 megawatt scale. We're looking at around about similar prices to offshore wind. However, we see that's our entry point. Like every technology, we believe that there's opportunities both through scale and also through learning to carry on driving those costs down as we move further and further towards, I suppose, the traditional fossil fuel prices. But our entry point is around about the 117 euros a megawatt. In terms of our business and how we've achieved what we've achieved, as a business, we would have raised 52 million euro since 2004 over 4 investment rounds. So we've raised a considerable amount of money, predominantly private equity, and that would either be through high net worth investors or through some institutions. So, for example, Philip Lynch's 151 would hold a shareholding in Open Hydro. There's a major Canadian company called Emira that holds a shareholding in Open Hydro. So a mixture of both corporate and individual investors. And that money has been spent in doing this development, developing this technology and the research work we've done in Scotland. However, we need to continue to scale our business. We've got what we believe is a global opportunity for Open Hydro. We've got an enormous resource globally in tidal. We also have a very much a leading position within our sector. So we're currently raising further funds in our business. And the principal reason for that is just to scale our organisation, to give ourselves the capacity to deliver more of these projects and to grow our business. So that was really what I was hoping to present to you today. And I'd be delighted to take any questions that you have.